Yeah, good morning. Good afternoon, everyone in the US, and good morning for people in Taiwan. And thanks for joining me for my dissertation talk. The topic of today's talk will be negative capacitance field effect transistor design and machine learning application in compound model. And I chose this cover photo because this is very similar to the path of my PhD journey, a few downturns, and eventually we get some improvement. So this will be the storyline, the outline of the storyline throughout my PhD, and will be the outline of today's talk. This color actually was inspired by, I just started to learn how to snowboard, and this color is corresponding to the color difficulty in ski resort. Green one means the beginner level, and the blue one means intermediate level, and the black one is the advanced one. Then let me get started from the very first, the course and learning. So I'm going to talk about a few of my course experience, and GSI. This is abbreviation of graduate student instructor at UC Berkeley. And I really appreciate there are a few inside courses. I really appreciate those course instructor that teach me the fundamental and on my inside major and help me better prepare for my future research. And I also going to go through a few of my outside minors, like the first one, the introduction to financial engineering. Though it is not quite related to my research, it really have some impact and open up my interest toward personal finance and investing, and better help me prepare my personal finance and career planning. And the next two, artificial intelligence and data mining, it also not quite relevant at this point, but it really, I really connect the machine learning application in the compound model in my last year. And I also appreciate I also got the opportunity to serve as a graduate student instructor in these two courses. Integrated circuit design was led by Professor Saeed Salahuddin, and also this applied data science. This experience helped me, let me have the opportunity to interact with the juniors, undergraduate students, and practice my presentation skill, and also have the very valuable chance to guide the undergraduate student for their group projects. And before digging into my research, I'm going to talk about a few background knowledge to help you better understanding what I'm doing and what I'm talking about. Moore's law, TCAD, BSIM, and NCFET. Okay, so the quote from Gordon Moore, the founder of Intel, and he said that the computing power will double every 18 to 24 months, and it did happen, and so it became computing power doubles every 18 and 24 months. If we look at the left-hand side figure, the y-axis is the transistor count in log scale, and the x-axis is the along the years. You can see some a few famous brands like AMD and Apple A13 chip, which is the inbuilt chip for iPhone 11 Pro, and the very first Intel Platinum. And if we plot those products on this plot, we can see this line, a line on the log scale plot, which means it is exponential growth. It's really follow what Gordon Moore said, the computer power grows exponentially along the year. And to achieve this, I show three biggest foundries, the semiconductor producer here, TSMC, Intel, and Samsung. And they are trying to do their best to scale down the transistor, as you can see at here, the bottom left figure, 113 nanometer down to 65 nanometer and 22 nanometer. And you can see that it is the scale down really is impressive. This 22 nanometer, if we put this one in this 130 nanometer, is that scale is very impressive. And to keep developing the technology, before these foundries put their design, the transistor design into fabrication, they have to run some simulation to make sure their transistor design is physically correct. So that's how the technology computer-aided design come in. The abbreviation is become TCAD. And the TCAD simulation basically is composed of two components. The first one is we have to build the geometry. The transistor designer have to build the geometry virtually in the computer. And second, they have to choose which physics equation they would like to include, and the computer, the TCAD simulator, will solve those physics equations self-consistently along within these grids, and can give out the target transistor characteristic. And if the transistor characteristic that's simulated comply with their expectation, then they can put in the trial run in this fabrication. And once those foundries develop a good new technology, they have to deliver that information, what's included in that new technology, in the form of this called PDK, the process design kit. And that PDK is composed of the company models, first one, and the second one, the model cards. So what is a company model? The company model basically describe a behavior of a transistor. And Berkeley, the BC model is the first industry standard company model developed right here at UC Berkeley. And that is abbreviation of Berkeley Short Channel IGFET. IGFET is insulated gate field effect transistor model. So BSIN is called BSIM. And the BSIM model architecture looks like this. We have the core model. The IV means the current versus voltage, and the CV is the capacitance versus voltage for the SPICE simulator. And we also have the peripheral models for the non-ideal effect. And it has around 8,000 lines of code, which is a very complete model. And once the foundry used the PDK to describe their new technology, they will send it to the fabless circuit design house, some big name here like NVIDIA, AMD, Apple, and Qualcomm for their ASIC or GPU, CPU design. Okay, so I'm going to talk about next will be the NCFET. That is a very frequently appeared term throughout my research topics. So I have to explain what is the NCFET first. So we can split NCFET into NC and FET. NC is the negative capacitance, and the FET can be represented by this field effect transistor. And let's talk about what is a FET first. A FET, the field effect transistor, it's like a switch, and it's composed of at least 3 terminals, the source, drain, and gate. And we have the carrier like electron flowing through this channel, and this channel can be controlled by the gate. The gate can decide whether this channel is on or off. If the gate control is off, then for example here, the bottom left figure, the drain current, which is a current flowing through here, and the gate voltage, which is a bias of this gate control. At the offset, BG, this gate voltage is equal to 0. And you can see the current is orders of magnitude lower than the on current, which is the current here. So it's like a switch, basically. And after knowing what is a FET, and let's talk about what is the NC, negative capacitance. If we plot the dielectric, this parabolic blue line here on this energy y-axis versus the charge x-axis plot, and also along with this ferroelectric, the black curve, this double valence curve, And in nature, if we put this ferroelectric alone, it will stay at the minimum energy, so the charge will not be zero. But if we can create a system with the dielectric and ferroelectric, well designed like this red curve, we can stabilize our state at zero charge, and we call that depolarization, or we have a good capacitor matching condition for NCFET. And we know that the derivative of energy with respect to charge will be voltage versus charge. And then we plot again the black double valley curve here. The derivative of this double valley will be this one, the same color. And the blue parabolic line will be this linear dielectric capacitor. And the ferroelectric is a nonlinear capacitor. And within, we just said that we can stabilize the at zero charge. So it's possible that we can stabilize here. And if we can operate our transistor within this range, this red box, we know that the derivative of charge and voltage will be the capacitor. And we saw this negative slope, which means there's a negative capacitance region. If we can operate our transistor, our field effect transistor within this range, we can make use of these negative capacitance benefits. And I'll talk a little bit more about how we could make use of that negative capacitance in the next slide. So I copy this conventional FET, the basic structure here. Then let's say that our dielectric, I use DE to represent the dielectric, and the insulator is a dielectric, is 1 nanofarad. And we also have compared with the NCFET here. And in addition to this structure, we have the ferroelectric on top of this dielectric. And I would like you to remember that this Fe is representing the ferroelectric and De is representing the dielectric silicon dioxide insulator. I'll use this abbreviation many times along this presentation. Yeah, so the same structure. So we have the same DE capacitance, 1 nanofarad. And remember, we have the, if we operate our transistor appropriately within that red box, we have the negative capacitance, and that simplifies it to be the fixed number. Let's say it's minus 1.5 nanofarad. And the total effective capacitance will be 3 nanofarad. Use the inverse sum and do the inverse. And that total capacitance, 3 nanofarad, is much larger than this dielectric capacitance. And we know that the larger gate capacitance could have, will have the improved gate control, because by looking at the simplified circuit, we have the gate voltage here and the CFE corresponding to this ferroelectric layer, and the silicon dioxide capacitance corresponding to this insulator. And this psi S is the silicon potential. And if we have a larger gate capacitance, the equivalent capacitance of CFE and SiO2, then the gate will have more control over this silicon potential, then will corresponding to better channel control. So that's the benefits of NCFET. So after knowing all the background knowledge, I'm going to talk about the first project, the first research topic, NCFET variation. And I would like to give you a big picture of what this research topic is. So basically, we can see there's a geometry here. We have the source and drain, and the gate control is a double gate structure. And the blue region is a channel. So the gate could control whether this channel is on or off. And we have a few grids here. And I'll explain later on, but we can say there is some impurity here. The ferroelectric, some grids in this ferroelectric film is not ferroelectric. Instead, it's a dielectric. So those dielectric impurity will affect the performance of this NCFET and cause some variation. So let's start to talk about the assumption in this research. And the first assumption, they are dielectric grains in ferroelectric film. If we look at this Riemann polarization versus the monoclinic phases fraction, here we need some Riemann polarization to have the characteristic of FE to make use of the NC. So we have to have some amount of that. For example, we need 20 here, 20 microcoulomb per centimeter squared. And there will be a corresponding monoclinic phases fraction like 20%. And monoclinic phase is not a ferroelectric, which means it's it is a dielectric phase. So that if we want to achieve 20 microcoulomb per centimeter squared value here, we have to at least have 20% impurity in our ferroelectric film. And that's how the impurity come in. And the second point is that we have to know how large the grain is because we have to design our geometry for the simulation, right? And in this plot, this is a grain size versus thickness plot, and we can see the trend that for this half-ring zirconium oxide on two different metal base, the trend is roughly, the grain size is roughly at the same magnitude as the thickness. So we have the 2 nanometer thickness, and the I'll talk about the length and width. It will be 6 nanometer length and width, and you follow this, basically follow this trend. And we would like to study how much variation will this DE, the dielectric grains, contribute to the performance and cause the variation in the performance of NCFET. Okay, this is our, we propose this simulation scheme that we cut the gate stack into different grids, and we have the source and drain and the channel. And like the simulation said, we have 1/3 of these grids to be dielectric and 2/3 to be ferroelectric. So which means that for the top gate, we will select 3 out of 9 grids to be dielectric impurity randomly. So we can run the Monte Carlo simulation on that. And the grain size is, we just mentioned that, I just mentioned that 2 nanometer by 6 nanometer and 6 nanometer. And we also have to know the parameters for the ferroelectric. So we did the parameter extraction for that. We have the blue symbols here is from the literature measurement data, PE curve, PE loop for the ferroelectric. And we know there are ferroelectric and dielectric phases within this ferroelectric film. So we have this green line representing the dielectric phase and the black line represent the ferroelectric phase. And the weighted sum of this black and the green will be this red one, and it fitted on this literature data very well. And we have the parameters for the ferroelectric now and geometry, so we can run the Monte Carlo simulation. If we look at this plot, the y-axis is the on current and the x-axis is the off current. And this pink circle is for the baseline. It's not an NCFET. And the blue triangle is with a pure ferroelectric NCFET. And we can see there's a off current reduction and on current boost, and that's a benefit of NCFET. But right now we have the impurity, right? So there are variation due to those impurity. We can study how much variation, and we can design our transistor to let that variation within our expectation. And our simulation results show under that geometry scheme and simulation scheme, we will have 30% off current variation and 14% on current variation. Yeah, that's the first topic. And at the end of the first year, I took the preliminary exam. I would like to acknowledge a few people that the oral preliminary exam, and I got a grade overall 9/10. I really happy with that results, and I would like to say thank you to my study group, Yuhong, Xiaoer, Savang, Adi, and Jason. And we studied for the whole month up to 1.5 months, and we have 3 times meeting per week, and we study really hard. So eventually we all passed through this oral preliminary exam. And I would also like to say thank you to Professor Salahuddin, Professor Arias, and Professor Boker. Without their challenge, without their oral preliminary exam challenge, I cannot better prepare my research foundation of knowledge. So the start of the second year, I'm going to talk about the second project, optimization of NCFET. We saw this simplified circuit before, and I'm going to talk about the motivation of why we are doing that in these slides. And we know that this is the equivalent circuit equation, 1 over the inverse of the total equivalent capacitance will be this inverse sum. And we can further, with this blue box, we can equivalent the 1 over silicon dioxide and 1 over silicon to be represented as a CMOS, which is the capacitance of the MOSFET. And this CMOS will vary with the position along the channel. As you can see in this plot, the capacitance along the channel, we have the different bias condition. On-state is this red one, and the off-state is this black curve. And that CMOS value is changing along the channel. And we also would like to, I would like to also to introduce you the capacitance matching condition. So to maximize the C total according to this equation, we have to, this absolute value of the inverse of the CFE should be smaller and as close to the this inverse of CMOS as possible. But right now we are looking at the not the inverse one, we are looking at the CFE and CMOS. So CFE should be larger than and as close to the CMOS as possible. So we plot this CFE as a fixed value here, and it has to be larger, right? So it cannot be crossover with any bias condition CMOS. So this is our this is the optimized capacitance matching for this benchmark, the conventional NCFET. And if we look deeper into that, we will see there's a fringing capacitance. This black arrow on this plot represents the electric field from the corner. And due to those electric field, we will have a non-uniform capacitance along the channel. As you can see, we have larger capacitance that we call fringing capacitance from those fringing fields. And we propose this design. We will have thicker silicon dioxide at the edge and thinner at the center of the channel. And by this possible potential process technique, thermal gradient or max oxidation, we can achieve this design, transistor design. And by having this our proposal design, we can have this more uniform profile of the CMOS on this capacitance versus along the channel plot. And so that we can further optimize our capacitance matching. This green and with this center region is very far compared with this blue one and this red curve. We can see the overall capacitance matching condition is improved. So this is the results for drain current versus gate voltage. We have the black line, which is a baseline. It's not an NCFET, it's a normal FET. And the red one is the conventional NCFET. And the blue one is our proposed NCFET. We align the off current together and we can see significant boost of the on current. It's a better results with our proposed design. And the next topics, I'm going to talk about the NCFET on IRDS roadmap. Before I have to explain what is the IRDS. IRDS is an organization and it is an abbreviation of International Roadmap for Device and System. And that organization gave out the specification for circuit designer and the foundry and related VOSI, a very large integrated circuit field, related people to know if they follow this spec, then they could potentially follow the rule of the Moore's law. So this organization which organize people from different subfield of VOSI to further improve the performance of the computing power. And if we look at this left-hand side figure, we can see the development of the transistor architecture along the year. We from the planner and we like 10 years ago we transitioned into the FinFET. The FinFET is developed here at Berkeley, And we are very probably we are in transition into the GAA, which is a gate all around. You can see this red gate is wrapping around the channel, which will have a better control over the channel. And for this study, we would like to study how much the NC could benefit this FinFET and GAFET scaling on according to this IRDS roadmap. Okay, so to study, we have to first build our baseline device. For FinFET, we calibrate to IRDS 5 nanometer node, and for GAFET, the gate all around FET, we calibrated to 1.5 nanometer node. And with our baseline device, we also have to know what is the reasonable NC negative capacitance parameters. And these black square symbols are from Professor Salahuddin's group. They are real measurement device, and they also use the SEM, scanning electron microscopy, to measure the architecture geometry of their device. And I replicate this IL, the interfacial layer thickness, the silicon dioxide thickness, and the ferroelectric thickness, the same as their real device in the TCAD simulation. And this alpha, beta, and epsilon Fe is the ferroelectric parameters. So I can use these ferroelectric parameters and this match geometry with the real device to match this measurement data. And so we have the extracted Fe parameters. Then we could put this Fe on in addition to the baseline device so that we could see how much benefit could contribute on this scaling journey. So first of all, I would like to talk about FinFET. This is a table from the IRDS. The first row is the IRDS nodes from 5 nanometer node, 3 nanometer node down to 0.7 nanometer node. And the year of production 2020, 2022, and we are here 2022, right? And projection to 2034. And physical gate length also given, and the fin width, which is the thickness of the fin. And the IRDS is IRDS target VDD. The VDD is the representation of the supply voltage. So we have to keep reducing our supply voltage to save more power. So we will have more battery life on our iPhone and laptop. And the sixth row is the target. So under all above this, the 7 and 8 row, 7 row is corresponding to the baseline device, and 8th row is corresponding to the NCFET. And these two devices have to hit this ion target to say that, oh, we achieve this row, we achieve this node. So if we look at the 7th row, this 0.93 at 3 nanometer node for the baseline device can still hit the 3 nanometer node, but the following two nodes, it failed to hit the targets. And for the 8th row, with the NC, the benefit of NC, we can scale 2 more nodes. That's a 6-year extension in the year of production, which is impressive. So in short, so NC can help extend 2 more nodes. So baseline cannot be achieved on this 2.1, 1.5 nanometer node, but with the help of NC, we can achieve on the FinFET device structure. With NC, we can achieve 2.1 and 1.5 nanometer node. And these two nodes is not achievable by both NC and baseline. I'll talk about in the next slides. We can achieve it by GAA, the gate-all-around transistor. So for the GAA results, it's similar to the previous tables, but right now the first row is a year of production, and the second is node, and the baseline is calibrated to 1.5 nanometer node, right? And this is a baseline. This second last row is a baseline, and we have to hit this ion target to say that we can hit that requirement of that technology node. And with the help of NC, we can achieve all of them. But for the baseline device, we stuck at this calibrated 1.5 nanometer node. So NC can help extend 3 more GAA FET nodes on according to the IRDS spec. That's 9 years of extension of this scaling. And by the end of the third year, I took the qualification exam, and I would like to say thank you to the committee members, the Professor Chen Minghu and Professor Saif Salahuddin, Professor Ali Javi, and Professor Jun Wu. With their guidance, they check on my first to third year of PhD research and give me some feedbacks and guide me through the future research direction. And it's really helpful. And I'm really glad that my hair is still there. And I would also like to mention that at that point, that's a transition point from the in-person research and meeting to the online Zoom meeting. And because of the COVID-19 pandemic, so the following research are all done by remote. And the first project in after the fourth year, I'm going to talk about the NCFET campaign model. And I'm going to keep it short, so I list a few enhancements of NCFET campaign model here. We know what is a campaign model, right? And we know what is a NCFET. We know what is NCFET, and the combination of that basically means we build a campaign model for NCFET. And that NCFET model started by one of the senior, Juan Duarte, 5 years seniors than me. And I keep doing some enhancement on the model to make it complete. And the first enhancement is that I improved the initial guess. And why does the initial guess is important? We can look at these Newton methods. If we want to solve this blue curve and the y equal to 0, which is the intersection with the x-axis, we have to run the iteration, if we do the numerical simulate methods, and we start from this x1 and have the slope corresponding to x2 at 3, the same methods, our iterative solution will be closer to our final solution. And at x5 is close enough to our final solution, and the iteration will stop. And I improved that initial guess. And if we take a look at these campaign model equations, those equations we usually solve a few more nonlinear than in this illustration. And if our initial guess is not good enough, then our simulation will not converge. Our iteration will not converge. So I basically improved that initial guess. And as long as the NC negative capacitance matching condition is valid, the model can give out a reasonable solution. And the second enhancement, I added the dynamic terms. If we look at the bottom right figure, the lattice structure of let's say Fe, the half-radium zirconium oxide, and we can imagine that if there's some deformation and stretch on the lattice, we can use this model proposed by also one of the senior Korok, this dipole and spring model. And I implemented this model in our NCFET campaign model by using subcircuit of inductance and capacitance and resistance to mimic the behavior of this lattice dynamics. And the third enhancement, I implement the so-called polarization gradient effect in the ferroelectric. The polarization gradient effect basically is the interaction between the dipole in the ferroelectric. So for the neighborhood, they will have some interaction forces, and so that the changing of the polarization will be continuous with the neighborhood. And I implement that into the model. And if we look at this plot, we have different color, right? They are on the different bias. And the dashed line, the solid line is with a smaller polarization gradient effect from the TCAD, the symbol are from TCAD. And this, under this dashed line, the symbol also from TCAD, but with a little bit larger polarization gradient effect. And you can see our model with tunable G parameter, G represented parameter for polarization gradient effect. With tunable G, we can fit it to the TCAD data with different polarization gradient effect, which means our NCFET campaign model can capture that effect, that physics effect. And those are the three enhancements I I would like to mention for my contribution to NCFET campaign model. And next topic is about energy study of the NCFET. And we saw this plot before of this energy versus polarization plot of the ferroelectric, this double valley shape profile. And we know that if with good capacitor matching condition, then we will, with a valley capacitor matching condition, we will stabilize our offset here at zero charge, zero polarization. And for the onset, it can go down to here. And to better illustrate what's happening for the interaction of ferroelectric and dielectric, let's look at the this stack on the right-hand side. In the transistor turning on from the offset to the onset, there's some outside energy source to charging the dielectric, but also in the same time, the ferroelectric will try to release the energy and charge dielectric. And for the turning off process from the onset to the offset, there's a radiation of energy outside of the dielectric, and also the ferroelectric will try to recycle the energy back. And that's how NC could save some energy in this operation. And if we see this energy per switch, we can think of this as energy consumption per clock cycle in the computer. And the x-axis is a delay, is the inverse of the speed. So more delay means less, the computer is slower, and less delay means the computer is faster. And we can see the trade-off under the same technology. That's this black line with more delay, slower computer, we can save more energy, and with faster computer, we will consume more energy. And this black is a high K with a high K stack, which is a baseline. It's not an NCFET. And the blue one is a NCFET with good capacitor matching. So you can see that under the same delay, the blue one had consumed less energy compared to the black one. And if we also consider the peripheral parasitic capacitor and resistor, and we can see more benefits of the NCFET, the gap under the same delay, the energy gap is even more. And from as professor who mentioned in the beginning, I did my internship in the summer from my 4th year to 5th year. And what's the most well-known for NVIDIA is AI, right? So I start to think about what I can do to apply the machine learning to our campaign model. So the last topic will be potential machine learning application in campaign model. There are 2 subtopics. I'm going to talk about the first subtopic is the deep learning base for the campaign model parameter extraction. And what is a parameter extraction? So basically, once the foundry have the new technology, they will deliver this, we just mentioned the PDK, the process design kit. It is composed of 2 components. The first one is campaign model, and very probably for TSMC, it is a BSIM base, and plus a model card which stores all the parameters value for this transistor technology. And I would like to illustrate what is the parameters value to you, that if we look at this very simple equation, y equal to ax plus b, this equation, we can say it is a very simple model corresponding to campaign model. And this coefficient a and b are coefficient and or parameters. So we can say this a and b value will be stored in this model card, and this equation will be stored in this campaign model. And that's how the, of course, the PDK will be, the campaign model will be much more complicated than this equation, but basically the concept is this. And the, for example, TSMC can send out this PDK to the, let's say Apple for their design of the N1 chip. And before sending out, they have to run this parameter extraction to make sure the campaign model describe their new technology in a good way. And that parameter extraction require experienced human because you can imagine there are 1,000 parameters in the BSIM model, and it really requires the experience and knowledge of how to do the extraction, how to decide those parameter values, and it's time consuming for different geometry of the device. So if we could have this kind of machine learning, deep neural network assisted parameter extraction tool, that will be that could save times and human resources. And so we select a few BSIM parameters based on our domain knowledge. Those selected parameters are the parameters we think are important and crucial to the parameter extraction. And we can run the BSIM simulation and randomize those selected parameters within the range. And we can generate also the corresponding output of the BSIM model, which will be the IV, the current versus voltage, and the CV, capacitance versus voltage results, corresponding results. And we can do the reverse process and feed in this deep neural network for training. The input will be the output of the BSIM simulation of those randomized simulation for the training data. And the output will be the corresponding BSIM parameters. So basically, we are training the model to do the reverse process of the BSIM simulation. That in the training stage, the model is solely trained by the training data produced by the compound model. And we can use the silicon data to do the inference. And once the silicon data is a measurement of the IV and CV, to feed in as an input as the same format as we train, and we can get a parameters extraction result in a second with a very efficient inference by this deep neural network. And for our purpose, we use the TCAD technology, computer aided data, because we don't have the silicon data. We use the TCAD data for our inference and testing. We have 5 different cases, the baseline and some variation. We want to make sure our model works. So we do some perturbation, minus 10%, plus 10% in the effective oxide thickness, which is the thickness of the gate oxide, and plus 10% and plus 10% of the gate length perturbation. And we can see the parameter extraction by this deep neural network, very good fit to this. I'm going to talk about more in detail that the symbols are from TCAD and the line are from the parameter extraction result. And how we did that is basically we feed in these symbols into the deep neural network, and they will generate a couple of the parameter extraction values, right? And we feed in those values again into our BSIM simulator and generate this line. If they are lining up, then pretty well, then which means the parameter extraction results making sense. So we can see the very good match in this gate capacitance versus gate voltage and the drain current in log scale, linear scale under 2 different drain bias, and the derivatives also showing very promising results. So what I talk about for the first subtopic is a kind of a near-term machine learning, potential machine learning application. And the second subtopic is a longer-term goal. We could use the deep learning to help us we call that deep learning assisted IV modeling. Basically use the deep learning to help us to model the IV. We are not using the full complete equation-based model like BSIM anymore. We can use some kind of hybrid of the deep learning and the physics model in the future. And that could speed up the SPICE simulation time. I suppose it could speed up by an order, and I'll talk about it in more detail in the following slides. And for conventional compound model, that's a BSIM. It's an equation-based. There are some cons, limiting model, computation time speed up. With the scaling of the for the ultra short channel transistor, we need to add in more and more non-ideal effect, which will slow down the model. The BSIM computation time speed up can only rely on the Howard speed up which is the development of the Moore's law. And the second cons is that the complicated equation for the future technology is very difficult to maintain and make sure everything is right, and it's time consuming. And another group of people try to develop the pure machine learning model, and there are also some cons. Like that machine learning model, if there's not any equation in physics equation involved, there will probably be some non-physical behaviors such as non-zero current if the VDS equal to 0. If the input VDS equal 0, sometimes the model will give out a non-zero current. And this unsymmetric IV, we call it Gamow symmetry. And also, this is also very important, the variation modeling, which is in the transistor process, we usually have some kind of random variation, like in the oxide thickness and the channel length and the and any other geometry perturbation. And we have to model those variation because of some randomness. And for the BCM, since it's equation based, we have parameters, we can do some perturbation in the model card, and the corresponding results will also have some distribution. But for this pure machine learning model, it seems to be more difficult to achieve that. And is there any solution in between? And the answer is yes. We propose this hybrid model, this physics-based model. We retain a few core equation. If you remember, we introduced BCM, we have the core IV-CV model and peripheral non-ideal effect. We can retain the core IV and CV model. It could be 10 times faster, less computation time less than the complete model. And we all have the VGS, the different bias condition fit into that. And we will have generate this simplified BCM core model output. And we use a deep neural network as a correction function. It's a bias dependent function to correct this output, and it will be the factor of the multiplication. And after they multiply with each other, then this output will be fitted to our the measurement silicon data. So basically, the combination, the hybrid of this simplified model and these neural nets, the goal is to replace the BCM model, equation-based model. And I'm going to talk about a few benefits. For the cons of the ML model, this model, the IDS will be 0. This output will be 0 if the VDS equal to 0, because this is a physics-based model. We can guarantee that at VDS equal to 0, this output will be 0, and 0 multiplied by any factor will be 0. And the symmetric, we can also make sure this physics equation based, so the IV will be symmetric, and we can do some transformation here. The U1 and U2, there's a corresponding transformation. We can, if you take a look at it in more detail, if we swap the G and S, the U1 will be the same, and U2 will also be the same because there's a square here. And the third point, the variation modeling, we retain some BCM parameters here, and we can still do some perturbation to our L, the Galen and ELT, other geometry parameters, and do the same thing as the BCM, the equation-based model. And for some counts for the company model, the speed up is possible that for this downward, this bottom core equation is 10 times faster, and the upper can be done in parallel. And with the GPU acceleration, we could, this is only, if we have the GPU speed out, it's only the 3 layers, like 3 layers of the hyperbolic tangent function is very efficient. And this deep neural net can be trained to the future ultra short channel device. More and more non-ideal effects can be modeled by adding in a more complicated model here. For example, we can add in 1 more hidden layer or 2 more hidden layers to act as a non-ideal effect corrector. Yeah, so here is the results for that hybrid deep learning assist IV modeling. The cost function can drop across the epoch, different from more and more iterations. And we also show the IDS, VDS, the drain current versus drain bias and drain current versus a gate bias. That this black curve is the deep learning assist IV model, and the black symbols are from the TCAD, and they can overlap with each other very well. And also the derivatives, the GDS is a derivative of this plot, and the GM is a derivative of this plot. They can model very well, and if you look at the 3 sigma plot, it's super well. The 3 sigma is 1.3 for the current, and 3 sigma extreme case for even for derivative is down to single digit. Yeah, so I cover most of my these blue publication as the first authors, and I'm going to show the full publication list here. You can also find on my Google Scholar if you are interested in. And I would like to thank Professor Hu. I really learned a lot from him, and I would like to say 3 main points. First of all, he's very knowledgeable, and after passing through the prelim, I think I can like explain the different phenomena from textbook. But after rounds of group meeting, he can always look at the problems in a different perspective and from an interesting perspective, and explain my horizon of the knowledge. And second, he is also open-minded and a lifelong learner. As you can see that the machine learning project in my last year, and Professor Hu is willing to accept that project and advise me. He learns along the way. He also learned from doing. I also learned from doing, and we learn together how can machine learning apply to the campaign model. And I also learned a lot from his presentation skill. I remember that the first time I saw Professor Hu is at my senior years in a seminar in National Jiao Tong University. And I really impressed by his how he can explain a very difficult phenomenon in a very simple way. And I would also like to thank Professor Salahuddin. He is a life dictionary of physics in my mind. Whenever I don't know, I don't know of any phenomenon, I just go ahead and ask him. He can explain to me in a very clear way. And he also gave me very many feedbacks on my research and being supportive. And also thanks to all these people in these photos and my colleagues, my senior and juniors and postdocs. They mentor me a lot, and I grow a lot and learn a lot from them. And I also would like to say thank you to my wife Tianning, and she is beautiful from both outside and inside. She has a very kind heart, and she's not only supportive, she also always motivates me to explore the unknown and new things. Like we started to host a podcast last year, and we start to learn snowboard this year. It's really fun to staying with her. And this photo was taken at a year ago, 2021 January, on our wedding ceremony. And this photo was taken at in, I believe, June 2019. And I also would like to thank to my family, my mother, my father, my sister, and my sister's husband, and my mother-in-law, Tianning, and my father-in-law and Tianning's brother. And I also would like to introduce that there's a very strong Taiwanese student community here at UC Berkeley. It support it really keep my mental health very well by there are so many friends here, and this photo was shot 3 years ago before COVID-19 pandemic. I was president of Berkeley Association of Taiwanese Students, and I held a Tahoe retreat, and there was around 80 people there. We have all hold a restaurant. And I also would like to say special thanks to Professor James Harris from Stanford University and Professor Chu Wei Liu from National Taiwan University and Dr. Longten Wang, and they all supported my PhD application. Without their help, I cannot get into these programs and be advised by Professor Hu. Yeah, and that's pretty much it. And thank you very much for your participation. And is there any question you can ask? Let me take a look at the time. Yeah, it's almost hit the 1 hour.
That's a good time control, Ming-Yen, and thank you very much for this talk. It not only came from your brains, it also came from your heart. I certainly enjoy that. So would you be willing to stay a little longer to take some questions?
Yeah, of course. Yeah.
All right.
And before taking question, I would like to take a group photo if possible. Could a participant turn on your camera so that I could screenshot the group photo? Yeah, there are 2 pages, I believe. 3 pages. Yeah, I'll say 1, 2, 3 for the first page. 1, 2, 3. Thanks for staying there, and I'm going to save it. Caption 1. Okay, so next page, please stay tuned. Yeah, I think 2 pages is fine because not everyone turning on camera. And yeah, thanks for turning on camera. And 1, 2, 3. Yeah, I capture everyone's face. Yeah, thanks a lot. If you want to ask question, you can stay, but feel free to leave because it's over 1 hour.
Any questions for Ming-Yen? Any comments? He must have said some good thing about some of you in his talk.
Hi, Ming-Yen. Thanks a lot for the great talk. I have some questions about the LESS project that you introduced. So yeah, it's very interesting that you have a hybrid model, which is physics-based, but you can leverage the power of the machine learning. I'm wondering if you can comment on, how this hybrid model perform in terms of runtime, because it seems like you're introducing some additional layers of equations, and how does that affect the, let's say transient simulation in SPICE?
Yeah, we haven't did a really thorough testing in the SPICE simulator because, as you know, that this GPU acceleration feature is not enabled in the SPICE simulator probably by synopsis. We have to be developed in the future later. Right now, we only estimate the time benefits based on the computation time in this physics-based model. If we I did some estimation that the computation time is 10 times less, then I just gave out a very rough estimation here. It probably 10 times faster. And this will be the bottleneck, right? Because here the deep neural network can be processed in parallel in the inference stage, and this should be much faster than this physics-based model.
I think my question was more on the solving of, let's say Newton-Raphson. When we try to solve the system of equations at a very large scale, then it's kind of like we will have to do backward propagation of, also differentiating all these additional equations for the neural network, and then solve the latent variables that will satisfy the system equation at the same time.
Yeah, we haven't tested that part yet. Right now, we just did a very rough estimation.
Okay, yeah, thanks for the answer.
Yeah, thanks for the question.
Any other questions?
Thank you, Dr. Ming-Yen, for the wonderful talk. I have a small question. When you're talking about the non-uniform IL layer, I was just wondering, are there any difficulties in the fabrication for such a design?
Yeah, I think difficulty indeed there will be, and we just proposed a prototype, and there is this structure haven't been produced yet. So I will imagine that even though we said that thermal gradient and max oxidation could very probably could generate this profile, but there will also be some variation and randomness in process. So it definitely be some difficulty ahead, I believe. But we haven't fabricated this prototype yet, so I cannot comment on this.
I see. Thank you.
Thanks for the question.
Any other questions? Well, if not, let us all thanks and congratulate Ming-Yen again. Give him a round of applause, either real or using your comment button. All right. Thank you, Ming-Yen.
Thanks, everyone.
Congratulations.
Yeah, thank you, everyone.
Ming-Yen, if I may, on that interlayer project, the interfacial layer, I think it was one slide further from what you showed. It seemed like there were some kind of kinks in the IDVG curve, if I remember.
Yeah, you can see my slide, correctly. Right?
Yeah, it was.
Yeah, this one.
Like here. Yeah, do you know the origin of
yeah,
that? Like it seems there are two.
Yeah, one of the reviewer in our peer review process did ask that question, and so we took a deeper look into that, and it was because of this a better capacitor matching. As you know, the inversion will start from the source and to the drain. So the first kink is coming from this good capacitor matching at this region, and the second kink in this linear scale at around 0.55 gate voltage is happening because this starting of the inversion here. And that's the origin of the
interesting.
Yeah, and we really at that time I dig into the TCAD output structure and look at the physics in that and find out that that's the point.
Yeah, well, thank you for the answer. Very cool.
Thanks.
All right, it's more than 10 minutes past 6. We'll thank Ming-Yen one more time, and I'll close the meeting now.
Yeah, thank you, everyone. Yeah, I'll close the meeting, and yeah, thank you again.